Okay, everyone's hear me well? Are you hear me there? Yeah. Okay. So welcome everyone to our second BDK Tech Talk. The first one was about bindings. It was given by Thunder. In this one, I'm going to speak about silent payments in Bitcoin Development Kit. I'm nymius. I'm nymius. I'm a grantee funded by the BDK Foundation to implement silent payment support for BDK. You can find me in GitHub also as nymius. And well, the first question that I want to answer here is why silent payments? So at the core of Bitcoin privacy, there have been this idea of not reusing your addresses for a long time. And this process of not reusing your addresses requires you to exchange a new address each time that you want to make a transaction. And it's an interactive process that is not always feasible, nor desirable. And there have been different protocols proposed to avoid this interaction, but at the same time they avoided this interaction and didn't reuse addresses. They also uh, require extra space into the blockchain, so they costed more, and they also created a trackable fingerprint on chain. So silent payments is another protocol, a solution for this interactivity problem, at the same time that is providing the privacy of not reusing addresses, that doesn't create this fingerprint, and also does not require you to pay more fees to get these privacy features. At the same time, it allows you to protect the privacy of the sender and the receiver. And the only drawback that it has is that you have to compute uh, to do computations on each block on the chain. So it was initially thought to work on full nodes, but there have been advances to bring it also to light clients. So what is a silent payment? Well, a silent payment is a transaction with at least one pay to taproot output that was produced by the combination of data provided by the receiver and data coming from the inputs of the transaction. So what's the magic trick behind silent payments? Well, the name before proceeding with the math behind silent payments, I would like to show you some references so you can understand what I'm going to talk about. So I would use ECC to refer to elliptic curve, ABCD, little letters, to talk about private keys. And well, capitalized A, B, C, and D will be public keys, and I will use G to refer to the generator point of the elliptic curve. Here, if I show you this keeper, I'm referring with the first letter is the private key, and the second letter is the associated public key to that private key. So when we say public key, we are talking about the generator point times the private key. And just for you to know, the private key, little a, is just a number. In the elliptic curve that we are using in Bitcoin, is a very large number, but it can be any other number. And for yeah, someone is talking. Okay, I hear a little bit of sound. Could you please mute yourself? Okay, thank you. So, well, a public key is just a multiplication, a product of the private key times the generator point, and is also a point. So just keep in mind that when I'm saying little a, I'm referring to just a number, and When I say public key, I'm referring to a point. So the name of the trick is elliptic curve Diffie-Hellman. So the elliptic curve Diffie-Hellman is a key agreement protocol over an insecure channel. What does this mean? Is that when you have two keepers and you exchange public information with the other party, you can combine that public information with your private information to produce a shared secret that you can send over an insecure channel. So you're creating a new key that both party knows, and you can use that key to, for example, encrypt secrets or exchange information, but you can also that key to derive uh, a new key using a special function. In this case, for silent payments, we are using a hash function. So we produce a shared secret that is a point, and by using the hash function, we create later another point, another scalar, sorry, to get a point later. So let's move to the silent payment protocol. So here I have called the two parties receiver and sender. So that those are the two parties involved in a transaction. So I have now two keepers, and they by the perspective of the sender, they don't know the private key of the receiver. So the senders just take the public key of the receiver and combine them with their private key to produce this shared secret derived from the actual shared secret that I showed you before, this one. So they use that to create to map this point, this scalar to the elliptic curve, and in that way they get a shared secret. But with this is not enough to produce a silent payment. Why? Because if we use this map point to the elliptic curve, we will to produce a script up key. We will end up being able to spend as the receiver or as the sender that script up key, because both of us know this SS shared secret. So what the receiver does is that it also in silent payments shares a second keeper to lock the funds on the just to himself. So when the sender again is creating this shared secret, at the end of producing this shared secret and mapping that to the elliptic curve, it adds that to the second public key that the receiver has given to him. So in this way, we produce a public key that we can use to derive as a secondary script out key. And that script out key is the one that is going to go into the silent payment output. This, remember, is the perspective of the sender. But when we look at the receiver perspective, sorry, we have the sender. We don't know the private key of the sender. So in this case, the receiver just uses his private key to produce this secret, and this is the same secret that the sender has produced before. So it maps again that secret to the elliptic curve, and it uses that mapping to produce the final public key that is going to be embedded into the script up key of the silent payment output. And he does this to later go through each transaction in a block, trying to find if this script up key has been introduced in any output of each transaction in the block. Something that we can do here is, because we don't use the private key of that is locking of the public key that is finally locking the funds just to ourselves, we can remove that private key and move that to cold storage, for example, or to avoid avoid the leaking of that private key that is finally the one that is unlocking the funds to ourselves. And I'm going to also rename all these just to refer to the public keys and private keys that for the receiver it is used in the BIP. So when I here you can see that we have a keeper that is called scan and a keeper that is called spend. Both of them have a private key and a public key. So the private key of the scanning keeper is used to produce this share secret, and the public key, the only moment that we need the spending public key of uh, of the receiver is at the end when producing the final script out key. But this is all the information that you need to scan for a silent payment output. So now, what's BDK missing about silent payments? Well, BDK has a lot of features, but some of them are not very need a little bit change to work with silent payments. So one of them is the transaction building process, where usually in BDK you have first the parameters of the transaction. With those parameters, you will transaction template. With that transaction template, you can compute the fees and get an initial target for your coin selection. So after that, you coin select your inputs. And after coin selection, you introduce the inputs to the transaction. So you produce an unsigned transaction and you build a PSVT from that. Then you have to sign the PSVT. And once you have the signed PSVT, you can extract the transaction and sign and broadcast to the mempool. If you look here, I have used a bold line between PSVT and signed PSVT because there is the only moment that we have access to the keys that are used to sign the inputs of the transaction. But in silent payments, as I show you, you also need the private keys related to the inputs at the moment of after producing coin selection, because after you have done coin selection, you have to get all the private keys related to those inputs to produce the final silent payment output. So one possible solution for this could be to add fake outputs at the moment of creating the transaction template. Well, what I mean with fake outputs, in silent payments, the only possible output that you can produce is a pay to taproot output. So you can add pay to taproot outputs to the transaction that are not sending those funds to anywhere, and you can use them to just coin select the inputs precisely, and after that get a fake transaction that you can use to get the private keys of the inputs and produce the signed payment outputs that you are going to use finally into the transaction. So once you have these signed payment outputs, you can replace those outputs into the transaction. So that would be a way to do it. But again, we need to have these private keys available at the moment of getting the inputs into the transaction to produce the unsigned transaction. Well, another problem that we have is that in BDK we are usually using chain oracles to get the information from the blockchain, and they usually work with script key based interaction. So you create requests sending the script keys that you want to track, and the oracle retrieves you information about them. And in silent payments, as I show you, we don't know the script key of our outputs until we have look at the transaction. So we have to produce them by ourselves and then check if they are available in any transaction. So that's a problem because it's not the usual way of doing things with different clients that are available out there, like Electrum or Explora. So we have to rework this to compute the script keys each time that we are looking at the transactions. Another thing is that to get the private keys and the public keys of the transaction from the receiver's perspective, we have the transaction inputs, and as I said, we need the transaction input data to produce the silent payment output. And the transaction input data that we need to scan those silent payment outputs is contained into the transaction outputs that those transaction inputs are spending. So the data is embedded in the script up key, and there is the public keys of the transaction inputs that we are spending. So actually, to be able to save the data that we need to spend the silent payment outputs that we receive, we should be able to look at these script up keys and get the public keys embedded there. So what I showed you before, that we were using the receiver scan and spending keepers, and the sender just have this simple keeper. In fact, is a combination of all the private keys and all the public keys of the inputs of the transaction. So we when the sender creates the transaction, he must take all the private keys of the inputs that are available to produce a silent payment output in the transaction and combine them to produce the shared secret that is going to produce the final silent payment output. And the same is for the receiver. At the time of scanning for silent payment outputs into the transaction, he must add all the public keys in the inputs of the privouts of the transaction to get the share secret to be able to produce the script out key. So that's something that is not necessarily done for all the script out key based architecture that we have in BDK, because when you look at a script up key in the usual way, you just request the information. You must look at the derivation path, and then you know which derivation path you must follow into the private key to sign for that input. But when you sign in a silent payment setup, you have to collect all this information to be able to produce the final signature. So in BDK right now we have a trade indexer, and the indexer allows you to get this information, to look at this information from the transaction and see if the transaction belongs to the wallet or not. And to do that in silent payments, we will need to adapt a secondary parameter to get the privouts of the transaction that are going to give us the different public keys used in the inputs of that transaction. And the information that we need to store about these outputs is basically the open to refer to the original privout that we are spending. Also the label. In silent payments, you can add some information to trick the final code that you are showing to the public. So this information is also needed to produce the signature for that transaction output, and also the trick that we use to produce the script out key. That's the shared secret that we map to the elliptic curve, sorry. So this information needs to be stored together to produce the final, to get all the information that we need to produce a signature for that silent payment output. A third point that, and another point that is also missing in BDK, or that is a little bit different in silent payments in relation to BDK, is the key management. In BDK, we are used to handle the BIP32 derivation path that we use for keys. So we have this tree structure that is very common in a lot of wallets, and we also can produce the derivation path for the BIP84 and all the related ones to this tree structure that we are used to see in a lot of wallets in Bitcoin. And as I show you, for silent payments, you only need 2 keepers, and the good news is that you don't need to change the key management that you usually have for your wallet. So you can add a derivation. You can get both keepers from this using the same derivation path that we are used to. But at the same time, you have to keep track of all the labels that you have produced to your silent payment code. These tricks that I mentioned that change a little bit the silent payment code that you are publishing. And another consideration is that the first label, the label 0, is just used for change. So this is a little bit different to what we are used to in Bitcoin. And well, this must be considered at the moment of producing a library or a tools to work with silent payments. So now I would like to talk about what I have implemented for BDK. So I started building a library, and what I was using at the beginning was the Rust silent payment library, but then I discovered that it was not suited for my needs back then. So I take some code of the Rust silent payment library and I started crafting the library by my own. And I use that to produce the CLI tool that allowed me to get feedback of what I was doing. So I implemented this CLI tool that to test different flows in silent payment. The first one that I wanted to be able to produce was to send to a silent payment address, silent payment code, and the 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 following step that I took to work with silent payments was to also be able to store the information that I was receiving from the silent payment outputs that I was finding. So I also implemented an indexer in a similar fashion to what we have now in BDK. So the idea is to store all the information that I need to sign for a transaction output producing using silent payments to be able to get that information together to be able to produce a signatures later. So now I would like to list the different things that I should do from each side of the library. So in the library, what we have to do from the perspective of the sender was to get the scanning and spending public keys of the receiver, then to go collect the inputs, add all the private keys of those inputs together, produce the silent payment output that is going to be embedded into the transaction, and then create the transaction, sign, and broadcast. So those are basically the actions that we need to do to produce a silent payment from the perspective of the sender. And I implemented that in two structures. One is silent payment code, and the other is the XPRIP silent payment sender. So if you go to Bitcoin DevKit BDKSP, that's where you are going to find that code. So let me show you if we can. Okay, so here I have this structure where I store the version of the of the silent payment code and the scan and spending key together from the sender perspective. So we only have public keys here and also the network that we are using to work with us with that silent payment. Also, I have the XPRIP silent payment sender that is a structure that allows us to get different outpoints or the inputs that we are going to use in our transaction and the derivation path of those inputs to produce the silent payment outputs that we are going to add to the transaction. That's from the perspective of the sender. From the perspective of the receiver, for each transaction, we must get all the inputs and all the prevouts of the transaction to add together all the public keys to be able to produce the share secret and then the script up key. And for each transaction, we must check if there is any script up key matching the one that we have produced into the vector of outputs. And we must repeat a few times this check with labels and also to see if there are multiple silent payment outputs sent to us in the same transaction. And I implemented that with different structures and functions. So I have a struct pub key. That's a way to get all the public keys from the prevouts of the transaction. Then we have the scanner. That's a way to look for the script pub key that we have produced into the outputs of the transaction. This works just for a single transaction. And we put all the information that we need to sign for that signing payment output in this SP out structure. And finally, the SP indexer is a way to put all the information about the silent payment outputs that we have received together with a fast way to accessing them. So now I would like to show you what I have done in the code. So I prepare a quick demo to show you how the things that I have done work. Let me start sharing a different screen. Okay. Is the size of the font right for you, or do you want me to make it bigger? I can. That's better. Okay. So to avoid the problems that you have with live demos, I have recorded this. So I'm going to reproduce the screencast that I have recorded, but you can go to the BDK SP repository to just reproduce it by yourself in your terminal, and it's going to work. So in this way, I'm get sure that I'm showing what I want you to show. So let me start this. So first of all, I have been using Rectest in a pod. That's a tool that Thunder uh, created, and I have been using a lot. So thanks for that. And I use this to set up an environment in a pod, in a container. That's a way to get easily a Rectest node running on your computer to test different things. So this first part is not necessarily useful for signing payments, so I'm going to pass it really quick. So here, what I do is I have set up my Rectest node. I expose the environment variables that I need to interact with the Bitcoin CLI, with the BDK CLI tools. So first, I set up just a wallet, like any other, not a silent payment wallet, just one to fund the transaction that I'm going to send to the silent payment wallet. So I fund that wallet, and then here I create the silent payment wallet. So I generate the keys that I need for the silent payment wallet to work. So here I create two descriptors with this pattern, with this descriptor derivation path, and I create those script. In fact, are four descriptors. Two descriptors. One for the scanning key and the other for the spending key. And with those, I can create the signing payment wallet, and I can create a database storing this information for the signing payment wallet. So after that, with the tool that I have created, I can get the silent payment code without label. So I can produce the final silent payment code that I'm going to use to receive payments. And as I showed you before, to create a transaction that is going to send to a silent payment output, I need to get the keys before to add fake outputs to estimate the fees, and to also be able to produce to get the inputs to fund that transaction. So that's what I'm doing here. So I'm creating a fake address, and I don't need to. I'm just using the an address of the first wallet that I have created, because the wallet is a pay to taproot wallet. So I just need the pay to taproot address to create the output that I need to replace later. So that's what I do here. And well, I select the inputs here to find that PSBT. And after that, what I have implemented is a tool to replace the PSBT that I had created before, to replace the pay to taproot output that I have in the previous PSBT with the pay to silent payment output. It's just a pay to taproot output, but just to make the difference, I'm going to call it pay to silent payment. So I add that output to the PSBT, and then I sign the PSBT that I have replaced. I extract the transaction and I mine a block just to get it confirmed on chain. And finally, I run a scanner, a silent payment scanner. So I get the information that I need to the tool to find the outputs of the wallet. And here I have found the silent payment output that I created just before. And I can see that reflected into the balance of the silent payment wallet. So here I have sent 10,000 satoshis to the silent payment wallet, and I see them reflected into the balance of that wallet. And I can repeat the same process, but adding a label to the silent payment code. So here I'm going to add the 32 label to the silent payment code with this line. So it's just the same silent payment wallet, but now I'm using a different silent payment code to receive the payment. So I repeat the process. I create a PSBT and I replace a pay to taproot output with a pay to silent payment one. I do that. I replace the output. I sign the PSBT and then I extract the signed PSBT to produce a transaction. I mine that a block just to get the transaction confirmed. And finally, I scan again the blockchain. This scanning process is working with is recording the previous scan transaction, so it doesn't need to scan the whole blockchain again. So it just scanned the last block, and I found I found the different a different silent payment output that is related to the silent payment code with label that I have just created. And when I look at the balance, I can see that the balance has updated. So yeah, here I have received both payments to the silent payment wallet. So that's all for the demo, and I'm going to jump back to the presentation. Okay. So what I have shown you in this CLI example is that I'm capable of changing or transforming a PSBT with pay to taproot outputs to pay to silent payment outputs. I also able to scan silent payments with labels or without labels. I'm also able to get the balance of these silent payments. And well, the last 2 points are related to the third one, because indexing and persistence are the one that make this balance checking for the silent payment wallet available. So that's what the CLI tool that I have implemented is capable of. And the next steps that I'm planning to do for this tool, and to also continue working on silent payments for BDK, is to be able to create, fund, and sign PSBT with the silent payment outputs. So my idea is to allow the silent payment wallet to also sign and create its own transactions. And for that, I also plan to continue working on the different PSBT related BIPs for silent payments. So the BIP 375 is the one that talks about how to add new fields to the PSBT to work with the silent payments in multi-party environments. So that's something that I'm planning to work on. And I also plan to move this proof of concept that I have created here to a more production ready API. So it can be used by other applications. And right now I'm not using the LiveSec bindings of the, because LiveSec is also working on their implementation of the cryptographic primitives that we need for silent payments. So I'm planning to integrate that with the library that I have. And finally, for the BIP 375, we also need the BIP 374. And that's the one for DLEQ proofs. That allows you to check that because the BIP 375 is the one that allows you to create PSBT in multi-party environments, and the 374 is the one that shows you the proof that the other parties have created the shares that they need to produce the final share secret in the right way. So you get a proof that you are not going to send those funds to the void, right? So that's like a roadmap that I have to continue working on this. Now you can ask me whatever questions you have about this. So I'm open to answer. If you don't have questions, I have a few ones that I have prepared. Well, actually, there are two. These questions were asked me a lot. So, what is the support for light clients and how they can be integrated with compact block filters? So in the BIP, there is this note that says that a line client refers to any Bitcoin wallet client that does not process blocks and does not have a direct access to a node. So that's what we understand here for light clients. And what we want to get from what we need to do in those light clients is to source the data that we need to compute the tweaks, and to check if any of the outputs that we have produced are into the blocks that we are scanning. So a way to do this in a light client setup would be to, in this graph, you can see that we have a client server, but don't consider the server as a single entity. You can have multiple servers and you can make different requests to each one of them. So here the client gets the tweaks or the pieces of information that we need to compute from the inputs of the transaction. So we get those tweaks, and with our scanning secret key and the spending public key, we can produce the script up keys that we can get from those tweaks. So we produce a bunch of silent payment script up keys, and with that we get filters from we request the filters from other server or different servers, and with the filters and the script up keys of the silent payment outputs that we have produced, we can check if we have silent payment output sent to us in any of those filters, and after that we can get the block that belongs to that filter. So we get the block and we perform all the computation, all the checking for each transaction on our light client. So that would be a way to improve the privacy of light clients through silent payment outputs and compact block filters. Are you sure that you don't have any questions?
I was going to I was going to mention or comment, basically ask the same question that you've answered, but I was also wondering where you anticipate these servers to run or live. Like, do you anticipate this as an Electrum protocol, like HTTP or similar, or do you have any thoughts on that of like who's actually going to be building these key tweaks? Because I've done some work on like proof of concept, and the by far the biggest bottleneck is the computing the scripts for all of the keys that could potentially be in a block. And part of that reason, I think, is, I mean, there's a number of things like the constant timeness of SecP is one of them. And also the current solution, there's a guy that made this thing called BlindBit that serves the key tweaks, but it's over JSON. And so serializing to and from these data structures, like basically you get a string that represents a public key, and then you parse it as a public key when it feels like that could just be relayed as bytes to begin with. So I'm wondering if you've given much thought to that.
Well, actually, the answer is I haven't delved into this that much. I just know like this idea of how to do it, but I haven't looked at the like in terms of cost of computation of this compute SP outs function. I haven't looked at it, but what I have in mind was to produce just to make this flow into an HTTPS kind of API, like a REST API that you can get this information. And yeah, probably the most computational cost of this process is going to be on the computation of the script keys. Mm, but yeah, I think that I don't I'm not just right now. I'm not working on that right now. But as I'm approach it, I will probably talk with you to know what to do about this. So yeah.
Sounds good.
Any more questions?
Thunder asked one in the chat.
Oh, sorry, I wasn't looking at it. Oh yeah. So the labels are a way to tweak the spending key of your address. So let me go back in my presentation. So well, this is going slow. Okay. So labels are a way to tweak the spending key that you are showing to your sender, but at the end it's just another piece of information that you have to add to your private keys to end up signing the transaction. The idea is to, without leaking information about the sender, to be able to identify the different sources where you are receiving funds. So for example, if you publish a silent payment code for donations and you want to have two of them published in different places and you want to identify what payments came from one each of these silent payment codes that you have published. It's not something clever to do to just create another silent payment code with two different set of keys. So to reuse the computation that you are going to do for the scanning, what you want to do is to just trick the spending part of the of the silent payment code to make it identifiable, but without changing the underlying private keys and key pair that you have for that silent payment code. So you use these labels to identify the sources, and at the end, when you are scanning for the payments, is just another tweak that you have to add to your public or private key while you are scanning. At the moment of at the moment of signing is the moment where you tweak your private key with these labels to produce a signature. So it's something that if we were looking at the silent payment information that the receiver published, it could be like something like scan the public key of the scanning and spending spending with a little change into the it's not a little change because it's something that is also hashing and it also uses hash. So it's going to be really different to the original spending key, but the first part of the silent payment code is going to be the same. Any more questions?
There's another chat question about the address format.
How does this? Well, the first question, yes, there is a specific format for silent payments. It has been specified into the BIP. So it has different human readable parts like usual addresses formats for their kind of scripts. And the way to encode the information, the scanning and spending public key that the sender is going to need to produce the silent payment output is to add this human readable part at the beginning, then to add the encode spending public key, scanning public key, and the last bit of the address is the spending public key. So yeah, there is a specific format. And well, I suppose that the way to know that someone can accept a silent payment is because they have published this silent payment code, and you can look at the first human real part and realize that is accepting silent payments. And in relation to the third question, how does this handle BIP 21 where you can accept payments through URLs or BIP 353 for DNS? I haven't looked at those BIPs, so that's a question that I cannot answer. Sorry.
Stats to me link has some reference to number 3.
Okay, thanks. Great source. Okay, I will come back to my presentation, and if there are no more questions, I would like to thank you all for coming today and to the BDK Foundation to allowing me to work on this. So, well, that's all for now. Thank you all.
Thanks.